Okay, well, welcome everybody to this second week. Okay, apparently this school has been a little bit ill-fated in the second half. We have a brush with history, contemporary history. So the situation is the following. Due to the closure of the airspace in Israel, Vitaly Milman couldn't travel at all. So, and then we considered the possibility of having his lectures online, and in the end, we decided for not having that. He also suggested not to have that because he said, well, I might need to reach, the air bunker protection. And so there will not be, these lectures, the lectures by Milman will not be replaced. So the situation is the following. We will now update the schedule, let's say in the next few hours, but there will be 3 courses, one by Antonio, one by Michailis Morgoglu in presence, and one by Marianna Csornyei online. Oh, she couldn't travel also, not because of a whim, but because her university suggested, since she doesn't have an American passport, they explicitly suggested her not to travel because something. Okay, so apparently we have been really not very lucky. So this said, the schedule in the next days will be, okay, the schedule today will be that there is a lecture now, there will be no lecture after the coffee break, and there will be 2 lectures in the afternoon. Rest of the week, there will be a lecture after the first coffee break. So we start at 11, or if you prefer, 10:30 with a coffee break. There will be 1 lecture and then 2 lectures in the afternoon. Okay? For the rest of the week. And last but not least, remember tomorrow we will not be here. The lectures will be in the main building of the Scuola Normale in Piazza dei Cavalieri, Aula Bianchi room. Okay? So I think this is the most relevant information that you needed to get, and there will be probably other updates later. But okay, I think we can start. So we are a bit late, but apparently that's not a problem. Please.
So first of all, since I'm the first speaker, so first of all, let me thank the organizer for organizing this beautiful event. And it's always a pleasure to be back in Pisa. And yeah, so I think I can start with my course. Okay, so this course is devoted to the theory of varifolds. And we will do it in view of some application. To the min-max theory. And before going into the theory of varifold, let me explain a bit more what I mean by this arrow. So why will we need the theory of varifolds for to go into the direction of a min-max theory? Of course, min-max theory is a very wide topic. So what I refer with this is mostly the min-max theory for application in the min-max theory that is related to the minimal surface equation and to the problem of finding closed minimal surfaces in closed Riemannian manifolds. So let me start with a bit of history. So we know that classically, when we solve the Plateau problem, we can use several notions of weak surfaces as finite perimeter sets or currents. And the reason why these tools work so well is that if you define the Plateau problem in a very general way as the minimization of the d-dimensional area of d-dimensional surfaces which satisfy certain boundary condition. Okay, so here with P, I'm encoding some boundary conditions or homological condition. So this is a geometric variational problem. It's a problem in calculus of variation. As we know, two main properties to prove to get some existence of solution is to get a compactness of your class and lower semi-continuity of your functional, right? So, so we desire a topology which provides lower semi-continuity of the area. And the reason why currents and finite perimeter sets work so well, let me use just the notation of current, is that if you take your minimizing sequence in the sense of current for this problem, Tj, which given some good compactness property in the space of currents will converge to your candidate minimizer T, you have the property that the area of T, which in the sense of current is denoted as the mass of T as the lower semi-continuity, so you have that this is less or equal than the lim-inf in J of the mass of Tj. And so you can recover your minimizer. So you can show in this way that T is actually a minimizer of your problem. However, as I was mentioning before, in this course, we will deal with constructing critical points of the area functional. And in this procedure, so what is the idea? As I was mentioning, we will want to construct closed minimal hypersurfaces in closed Riemannian manifold. So if you imagine you have a sphere, okay, you would like to construct eventually yours as a solution, the equator, for instance, let's call it sigma. And we will be oftentimes in a situation in which we have a sequence sigma j, a sequence sigma j of d-dimensional smooth submanifolds let me say along this course, D will always be a number between 1 and n. So will be the dimension of my candidate object that I want to construct. So d-dimensional smooth submanifold. Okay. We will have some area bounds that tells you that this sequence is non-degenerate in the area. So we will have area bounds of the type that the infimum in J of the area of sigma J is positive, and the supremum of the area of sigma j is finite. Okay? And we will want to deduce that we have a limit in a certain sense will converge to some candidate limit sigma. Oh, something else that I forgot, plus sigma j will be almost critical, will almost satisfy the stationarity condition for the area to be almost a critical point. For the area. And we will want to pass to the limit this sigma j in an appropriate sense to recover a sigma, which is a stationary surface. Stationary here will mean a critical point of the area functional, stationary d-dimensional submanifold. So why in doing so we cannot immediately use the framework of currents? So you can imagine sigma j to be this guy, a parallel on the Earth that is converging to the equator. And if it was this one, currents will work just fine. However, there may be another situation, since we will not have much more control of what I'm writing here on this min-max sequence, there may be another situation in which your sigma j is something like this. Okay? So imagine that sigma j is the boundary of this finite perimeter set. Okay? So you will have these two orientation on the two layers of the boundary. So when you pass to the limit in the sense of currents, you can immediately see the issue that is happening, that your problem becomes degenerate. Okay, so you lose all the information in the limit. So what's happening in that specific situation, it may happen that sigma j converge to 0 in the sense of currents. Okay? So you may say, why is this not a problem in the plateau problem? So what is different from the plateau problem is here. And here, in the plateau problem, you have something that prescribes your non-triviality, that is the boundary condition, okay? So in the limit, since you have to recover the boundary condition that I was describing as this set P, this family that encodes some boundary condition or some homological condition, that implies in particular that you have something non-trivial in the limit, or if it allows to be trivial, it's because that's your actual solution, right? So you want it to be 0 in that case. But in general, you have some boundary condition that force your limit not to be trivial, while we don't have such a thing here, okay? So we don't like this to happen, but in that case, we want to recover in the limit that layer sigma. The other way to say this, another way to see this, way to see this problem, is that here, just very heuristically for now, but it will be very precise when we go to the min-max. When I write that this will be a min-max problem, okay? So it will mean that, let me do a finite dimensional picture. Of course, this is not a finite dimensional problem, but let me still do a finite dimensional picture. It will mean that you will have, okay, my picture can be arbitrarily bad along the course, but hope you will forgive me. So you will have this chain of mountain between a valley that is here and the valley that is there. So in the min-max theory, we will try to find this point that will be achieved by taking all these paths. Okay? So what we will do is we first, on each of these paths, we have a maximization problem. And then along all the paths, along all these points that maximize the height on each path, we will take the minimum and we will end up in this point, okay? So this is basically telling you in that in your space, in this case, in the space of surfaces, you will have two, let's say, variational problem competing with each other. One is trying to minimize and one is trying to maximize. As we explained before, as well, we didn't need to explain at the end. I'm sure you are all familiar with the calculus of variation. So here, this requires a lower semi-continuity of the functional. But for the very same reason, if you have a maximizing sequence, now the same property will require to achieve a minimizer or a maximizer. Here you will need lower semi-continuity, but here you will need upper semi-continuity. So this is telling us that the problem is forcing us to consider a functional that is continuous, okay? So we need continuity of the area. Okay, so this is our problem. So we need to find something, a functional that is continuous for we need a topology that gives continuity for our functional. And this is where Almgren began investigating the idea of studying varifolds back in the 70s. So he figured out that in the machinery that he wanted to develop for the min-max theory, he needed to consider such objects. And these are the objects that we will see throughout the course. And these are the varifolds. But now let me say how you would get to construct such objects. Because if we imagine that we don't know yet what these objects are, we can try to give some proposals to solve this issue. And a naive way to solve this problem so a naive idea is the following. I look at the picture that was on the board a while ago. So I had this sequence sigma j here that I want to pass to the limit to do this guy. Well, and I can say instead of looking at the limit in the sense of currents, I can take the limit in the sense of measures. And measure have continuity of the mass. Okay, so at least if you are in a compact set, so like, with appropriate assumption on the boundary, so you will have continuity on the mass, and this will preserve the limit sigma. Of course, this will appear with multiplicity too. But so the idea would be, well, we can consider HD restricted to sigma j, so the D-Hausdorff measure restricted to sigma j. under the assumption that I was mentioning before, so that we have an upper bound on a uniform upper bound on this mass, we know by weak star compactness that this will converge weak star to a measure mu up to subsequences. Thanks to the fact that, remember, I was assuming that the sup of HD sigma j is finite, plus weak star compactness. Okay? And I will get my candidate solution mu. But of course, now you will tell me, well, you want to show actually that this mu is HD restricted to sigma up to some density here, some f. Okay? The issue is in this problem is how do you impose eventually, how do you recover eventually that sigma is a minimal surface itself? So how do you enforce the criticality, the stationarity for the area for the limiting measure mu? And this is not an obvious issue because what does it mean in general for a smooth manifold to be stationary? Okay? So how do we get stationarity for mu? Well, how would you do in general for smooth manifold? So if sigma is smooth, let's say sigma is smooth, in general, what you do is that you say, well, for every x that is a C1 compactly supported vector field, let me say for a moment, from now on, that I'm on the Euclidean space, just for simplicity. It's a vector field from Rn into Rn. You take a one-parameter family of diffeomorphisms generated, phi t generated by x, that is just the identity plus tx, so for small t, for small t. So what you are doing is that you are taking your d-dimensional manifold, sigma, and you are deforming it using the vector field x. And what you usually ask to be a critical point you impose that the derivative in T of the area of the surface sigma deformed via phi t is 0. So you impose that criticality the derivative in T at T equals 0 of the area of phi t x applied to sigma is equal to 0. Okay? So let's try to do the same thing for a measure. Okay? Let's take our limiting measure mu. Okay? What does it mean for mu? Mu is our sigma right now. What does it mean to do the formation of mu through phi tx? It means that I will take phi tx and I do the push forward of using phi tx of the measure mu. I evaluate this in Rn so that I get the total mass of my measure, and I take the derivative in T. But the point is that this guy is always 0, whatever is the measure, right? Because this is independent of the problem you are starting with, because just for the reason that the push forward of measure preserve the mass, right? So this is always true. Because just for the very simple reason that okay, there is not much I deduce from this. So in a sense, the criticality for measure in this sense is not really well defined. And what is that we are forgetting here? What are we losing? What are we losing? We do a very simple picture. If this is your measure, mu, H1 restricted to this circle, okay? And your deformation is a radial deformation. Okay? Of course, when you start dilating this circle, but seen as a measure, you preserve the total mass. What is happening is that you are rescaling it. This is your new guy. But now this will be a bigger circle. C. So C is for the density. H1 restricted to a bigger circle, beta S1, where beta is bigger than 1, and C will need to be strictly smaller than 1. Okay? So you compensate for the length, the higher length with the lower multiplicity. So in a sense, we are forgetting the area factor, right? So the idea is that here we are forgetting to evaluate how the vector field X is oriented with respect to the tangent plane associated to your measure, okay? So we are forgetting about the area factor. So this is how then Almgren said, well, of course there were objects similar coming from PDE that were the Young measures, but this is why in this setting then people started saying, well, then let's fix this. Let's not just consider a measure in space, but also let's try to remember the tangent planes of your surfaces. And this is how people introduced the theory of varifolds. Okay, so we will say that, again, D will be a number between 1 and n. We will say that, and also from now on, I will work in Rn. The results that I'm gonna say right now are in Rn, but since they are regularity results, structural and regularity results, up to minor modification, they can be applied also to Riemannian manifolds. So it's not a big loss of generality. That loss of, let me add the name, much generality. So a D-varifold, a D-dimensional varifold in Rn a D-varifold in Rn is just a positive radon measure. Radon measure. On the Grassmannian bundle. On the D-dimensional Grassmannian bundle. Okay? The D-dimensional Grassmannian bundle is just the set of all the couples XS, where X is in Rn, and S is a d-dimensional linear subspace of Rn. So it's just an element of the d-Grassmannian. So right now, once I say this, I don't need to say much more on the topology, in the meaning that the topology for this space now will be just the topology, the weak star topology. In the space of measure. So when I say that Vj is converging to V as a varifold, it just means in the weak star sense. Okay? Okay, so these are the objects that in a sense should fix that problem. We will see in a second that they fix that problem because now you are encoding the notion of tangent plane. But before doing that, just coming back to the previous consideration of the min-max, again, if you have these two lines, sigma j, well, in this case, let me call them Vj, okay, where you have multiplicity 1 here and multiplicity 1 here. As a current, you are seeing basically a tripole of a support, a rectifiable set in the support, a multiplicity, and an orientation. In a sense, varifolds are just the same object, but removing the orientation. So you remove this orientation, and when you pass to the limit, so let's say that this distance here is 1 over j, when you pass to the limit, rather than recovering 0 as would happen, as we said before in the framework of current, here you recover just this guy with multiplicity 2. Okay? And the tangent plane here was always flat, here was always flat, so you get also the same tangent plane. So here you would get in the limit, in this case, H1 restricted to L, and then on the Grassmannian part, you will get the Dirac delta on this tangent plane. Okay? Oh, sorry, Thomas. Thank you very much. Thanks for the... Okay, so you recover exactly the same object. You recover exactly the same tangent line. And of course, as Giovanni was saying, you now gained the multiplicity. Okay, so for this object, let me give a bit of notation now because we will need to work with these guys. So let me introduce the weight of a varifold of V is just the map, the measure pi push forward V, where pi is the projection map that to XS in the Grassmannian bundle associate X in Rn. Okay, so your varifold is a measure on a product space. You push your varifold just in the first component. So you, in a sense, here just care of this part. So here, this would be pi push forward V. Okay? This would be the weight. And we will denote it often with this symbol. Mass of V will be denoting this guy. Okay? Any question up to now? Okay. So this is the weight, and also the area of your varifold, if you want what we will call the mass. This is important just because it will be the functional that for which I will want to show criticality. If you want, is the functional for which I want to fix the problem that we had just for measure in space, so the problem of not having a good notion of Jacobian, the mass is just the weight of the varifold V evaluated on the space Rn. Okay, so this is the total area of your varifold. And before going more further, let me just make a small example. Because here everything looks nice. I just want to show you that the two things that are the space measure and the Grassmannian measure don't need to behave accordingly to one another. They can behave completely independently from one to another. Okay? So, for instance, if you take this sequence of varifolds, Vj, that is, you take a line, let's say from 0 to 1, and here you build varifolds like this, a sequence of surface like this, where let's say that this height here is 1 over j. You put multiplicity 1 on this surface, on this graph, and let's say that this angle is 45 degrees. Okay? So when you pass to the limit in the sense of varifolds, well, clearly the mass here is uniformly bounded, so for sure you can pass Wick star to the limit. And the varifold will converge to H1 restricted to this line, to this interval 0, 1. But now there will be a multiplicity on this line because you have to preserve this mass. Okay? And this should be square root of 2. And you will have, in the Grassmannian part, you will have 1/2 of the Dirac delta on this line and 1/2 of the Dirac delta on this line. Let's say that, let's call this guy L1 and this guy L2. You will have 1/2 of the delta in L1 plus the delta in L2. Okay? So I'm just saying this to say that the macroscopic structure of your varifold, you can imagine this part as the macroscopic structure. It doesn't need to reflect the microscopic structure of your varifold. So they behave kind of independently. So you have this as the support of your varifold and the support of the weight of your varifold, and you will have this guy in the Grassmannian. And indeed, let me do just a small digression. These objects were reminiscent of other objects that were used in PDE a bit before, that are the Young measures, and they were used in PDE really to reflect, to study problem in material science, because the way you can see this object applied in material science is that the space component of the varifold reflects the macroscopic structure, I don't know, of this table. Okay, so it's flat. This is your tangent plane S0. But then if you look at the microscope, you will see that there are corrugation in your object, given by crystals or given by any kind of material. There will be corrugation. And this corrugation reflects on a local statistics of the microscopic tangent plane your surface is arranging, your molecules are arranging with each other. For instance, this is very typical of crystals, where you have the crystal structure push the local rearrangement of the particle to generate some specific orientation that gives these local statistics at infinitesimal level. Okay, so the two parts are kind of unrelated to each other, at least in this generality. Yes. Vj is, oh, sorry, yeah, you're right. I draw just a picture, but Vj, if you want to be very precise, is, let's give a name to this graph. Let me call it G. Okay. So it's a graph in R2. So Vj is just multiplicity 1 times, I'm just writing first the space part of your varifold, is H1 restricted to your graph, to your G? Yes, you're right. Gj. As Johnny is saying, this is of course shrinking both in this height and in this scale because I give rigidity for 45 degrees. And then I give, in the Grassmannian part, I'm giving the Dirac delta on the tangent space at the generic point x. So let me write an x here, okay, of Gj. S. Okay, so if you want, this is the disintegration of your varifold. This is dvj. To be very precise, you would write in this way. Okay, so the disintegration of your varifold is this guy. So you have this guy as a support, and as a tangent plane, you take exactly the Dirac delta on the real tangent plane you should have as a surface. And now we will see that this is a specific type of varifold that we will call rectifiable varifolds, but I will go to it in a second. But this is what you get. But this is a good point. So in general, this is not something that you can do just for this varifold. As you know from the disintegration theorem for measures, given that this is a measure on a product space, I can always disintegrate my varifold in the two components. I can always disintegrate my varifold in the two components. Disintegration theorem. So your varifold, a generic varifold dvxs, can be always disintegrated thanks to the projection map on the first component. It's a product space. So you can always write it as the mass of the varifold, the weight of the varifold in X cross a Grassmannian measure. Let's call it alpha X. Let me use the same notation so that I don't get confused then. Let's say mu X, so that I don't change 20 times the notation. Mu X on X, where this guy here is a probability measure in the Grassmannian, in the d-dimensional Grassmannian. So you can always do this. And let me make a comment that probably is trivial to most of you, but I think it's useful to observe this. So the dimension of the varifold is not given by this guy. Right? Sometimes it's easy to confuse. I've seen also in some papers. So the dimension of the varifold is not given by this guy, but is always given by this guy. In the meaning that if I give you this varifold, that is the Lebesgue measure, the two-dimensional Lebesgue measure, so the top dimensional Lebesgue measure, let's say in R2. Okay? And then on the Grassmannian, I take the Dirac delta on a vector, V. This is a one-dimensional varifold. It's a diffused one-dimensional varifold. So the space part doesn't matter. The important thing is in which space the Grassmannian is living. What is the dimension of the Grassmannian you are considering your probability measures, okay? So this varifold, completely diffused with, I don't know, this orientation at every point, V. Let me remove the orientation because there is no orientation. With this, I mean the line parallel to V, sorry. Okay, to be fair, let me call it a line. Is, yeah. So let me add it just because otherwise you don't see it. So this line on the Grassmannian and diffuse varifold in R2, this is a one-dimensional varifold, okay? And let me also make a comment on this fact that I was a bit annoyed by putting or not the orientation. So a way to solve this issue, not to be worried of putting the R or not, is that this is the D Grassmannian. You can always take the projective space the projective space, so in a sense you lose the orientation. Or if you want, you can consider varifold as even probability. Let's say if you are on the sphere in codimension 1, you can look at the for every vector you can give the same probability to the vector v1 and minus v1. So you can even you can consider this measure, let's say on the codimension 1 Grassmannian, to be writing delta L if V is a vector parallel to L with norm 1. You can consider delta L to be essentially 1/2 delta V plus delta of minus V. And so this becomes now a probability measure on the unitary sphere. I'm saying this just because I will use this identification later, like in the third lecture, I will use this identification for codimension 1 variable or one-dimensional. Because yeah, that's correct. So this identification, I will use it as Giovanni is saying, you can do it either for dimension 1 or codimension 1, because they are dual with each other. So hyperplanes are dual to unitary normals, to their unitary normals. So this works in codimension 1. And so you can, rather than considering a measure on the codimension 1 or dimension 1 Grassmannian, you can consider probability measure on the unitary sphere that are even, okay? Even measure that gives always same weight to V and minus V. Okay, just a small remark. Pretty good. So now, as I was saying, I will, these objects are not the one that we are really interested in. We are interested in the so-called rectifiable varifolds. What is a rectifiable varifold? Essentially a guy like this, okay? Essentially something that can be written like that. So a rectifiable varifold, V is, let me say, a D varifold, is rectifiable if and only if your disintegration reads as follows, as up to a multiplicity theta x. This is DHD restricted to sigma cross. Now, the important part is that for rectifiable varifolds, while in general the two parts, the Grassmannian part and the space part, have nothing to do with each other, for rectifiable varifold there has to be this link. So this is really the Dirac delta in the tangent space of sigma at the point x. Okay? And here, sigma, a couple of things that I must say. Sigma is derectifiable. I will say in a second. I mean, I know that there is rectifiability in this week of the summer school going on, but since I'm the first speaker, I should define what rectifiability means. I will do it in a second. This is rectifiable, and theta is locally finite. Finite in the meaning that the integral of theta is locally finite, in the meaning that the integral of theta in DHD restricted to sigma on K is finite for every K compact. Okay? Theta is a function from sigma to 0 plus infinity. Function with positive values. Okay, so this is what a rectifiable varifold is. The only thing that I'm in depth with you is to tell you what is rectifiability here. What does it mean sigma to be rectifiable? I'm sorry, because I probably everyone in the audience know it already, but just to be sure. And also because there are different definitions of rectifiability. So let's sigma rectifiability for me will mean this along this mini course. Sigma is derectifiable if and only if there exists a countable collection collection of continuously differentiable maps that goes from Rd to Rn, such that sigma up to a measured zero set is contained in the union of the images of Fi. So such that HD HD evaluated on sigma minus the union of Fi Rd with I from 1 to with I in n, this is 0. Okay. This is what we will mean to be rectifiable. Just one small observation. So this is not a mini course on rectifiability. There are much bigger experts than me in the audience. I just want to emphasize a couple of things that it's nice this property to have. It will be a nice property to start with in our geometric analysis consideration in the min-max. Why? Because rectifiability allows, in a sense, almost every point to have a good notion of tangent plane, which we will use to do first order calculus, which we will use to basically go back and forth from our varifold that is obtained by the GMT consideration to graphical consideration on these tangent planes. So we will use it to push the criticality for varifold to an equation, an almost equation on our graphs, okay, and get the higher order regularity theory for our candidate solution. Basically, we'll start really from here by writing our graphs on top of these tangent planes and deduce some higher order regularity property. Okay, so one small last remark in these considerations of the rectifiable varifolds that we will use later. If theta is integer valued, we say that the varifold is integral. If theta x is in n for v almost every x, v is said integral. And we will see that this integral varifold has some nice property of compactness under certain assumption. Okay, now with this introduction on the object that we want to use, I can finally tell you how we fix the stationarity problem that we had at the very beginning. So because now when I define the image of a varifold via a diffeomorphism, so if I fix a diffeo, we define image of a varifold of V. So if I fix a diffeo from Rn to Rn, so in your ambient space, okay? So I will define the image phi push forward of V. So this should be a varifold on the a d-varifold, so still a measure on the de Grassmannian bundle. So I still define it by testing with test function as an honest measure, okay? So this will be the integral on the Grassmannian bundle of what? So remember your picture. You had this guy. You wanted to dilate it to this guy. Okay? So this point here will be pushed here. But what was the other problem? We wanted to we want to remember how the tangent plane is changed. So you take the differential of phi, and we evaluated it on S. This will be our new tangent plane. And where is the correction that we add? This is obvious at this point. This is just the Jacobian of phi. Okay? At xs. Okay? And then this is integrated in dvxs. In such a way that if you want, you have a deformation that is orthogonal, the area factor is kind of maximized, while if you have an orientation like this, and you push in this direction, it doesn't change much. Okay? Just a small remark, what is the Jacobian? It's just if you want the determinant, so the square root of the determinant of the so I'm saying something. This is just square root the determinant of dx phi. Of course, we need to restrict it to S. Okay, so to our tangent plane. So it has to be a d-dimensional area factor. So this is why we restrict it to S. Transpose dx phi restricted to S. Okay, so this is the d-dimensional area factor acting on this plane via this differential. Okay. One other small remark. Don't confuse this guy, this image with the push forward, okay? This is acting on different spaces. So the push forward is acting on different spaces, while this guy always bring a varifold into a varifold, okay? So this is not to be considered as a push forward in the sense of measure, just because phi goes in from Rn to Rn. It doesn't even act on the right space to do a push forward in the classical sense, okay? So this is not defined on the Grassmannian bundle, phi. Okay, so it cannot be a push forward in the classical sense of measures. So there is no risk of confusion. Sorry? Well, yeah, so but then you would come back, if you lose the Jacobian, then you would come back to the problem. So then the varifold will be not relevant. So I totally agree. Then you can, this becomes, if you want, you forget the tangent component, but then you would go back to the problem of just taking basically the mass of the varifold and doing the push forward of the mass of the varifold via phi. But then we are again in the business that we don't know what criticality means anymore. Yeah, I totally agree. What I meant is that if you want, my comment was there will be no confusion of what this notation means, because if you will realize it from the domain of phi. Okay, just a small exercise for you, because unfortunately we don't have too many hours together. Exercise for you. Just check that if you take a rectifiable varifold, for a rectifiable varifold, let's say V equal to HD restricted to sigma, Tx sigma. I use this compact notation. The good notation would be the other one, the dV, but right now I think we understand each other what I mean. So for a rectifiable varifold, phi push forward V, exercise for you. This is just HD restricted to phi sigma tensor the Dirac delta in Tx phi sigma, okay? So it's really the push forward that the image of It's the same as first doing the image of sigma and then computing the varifold associated to it. Okay, and this is very easy. You just prove it. It's a change of coordinate essentially. You just prove it by testing with f. It's a change of variable. Okay. So this said, we can finally say what it means to be stationary for the area. So we will stay stationarity. So what does it mean for a varifold to be stationary for the area? It now will mean that be stationary if and only if for every C1 compactly supported vector field okay if I compute the derivative in t at t equals 0 of the mass of phi tx push forward v kappa, this is equal to 0. It's support of x contained in kappa compact. Okay, so this is now what it means. Sorry, I know this is a bit ugly to see. I just adding this kappa because otherwise, because my varifold doesn't need in general to have finite mass, right? So I wouldn't know what is the derivative in that case because it may be always infinite. Of course, if the mass of the varifold in Rn is finite, you are very welcome to assume kappa is equal to Rn. Okay, that's the only reason. So now this, for what we said, now makes perfect sense. These are very specific varifolds. It's not all varifolds that satisfy these, and these are the objects that we will get in the limit of our min-max procedure. Our starting objects for which we want to do some regularity theory. Okay. No, at this stage, if you want, at this stage, you don't know that. So actually, let me make an example. So this guy, so this definition, you can give it for every varifold. And indeed, if you take the varifold V, that is the same guy that I introduced before, you take the top dimensional Lebesgue measure in R2, and then you take the Dirac on a line, you can show that this is stationary for every line. These guys satisfy always this condition and is not rectifiable. So this property can be satisfied by many other varifolds that are not rectifiable, but I agree with you that from the stationarity, that is the equation that we will get out of the min-max, the geometric equation we will have in our GMT setting, we will want to deduce the rectifiability theorem, but this is a theorem that is true and is Allard rectifiability theorem for the area, but is true just, so we will deduce, I will do this in the course, but we will deduce rectifiability under, for stationary varifold, under the extra assumption, the assumption of a positive upper density. And this is sharp because of this example here. So you cannot remove this assumption, otherwise the theorem would be false and you have this kind of counterexamples. Also, I mean, we will prove this thing. The theorem can be actually localized. So you can also restrict your varifold to the set that contains these points, and that part of your varifold will be rectifiable. In a sense, the first variation, because these points split, in a sense, so it's a local result. So up to rescaling, the one of the two components will disappear, in a sense. So this result can be localized, but I will not go too deep. So I will just show the result as it is. Yeah, that's a very good comment. Thank you. I forgot. Yeah, actually, that's a that's a very good point. So that varifold is not stationary. So if you take this guy, the limit that is this with this tangent plane is not stationary. This guy is not stationary for the area. And now in the third lecture and a bit further, I will introduce anisotropic energy. The reason why it's more difficult you have complication for anisotropic energy is that, for instance, this will be stationary instead for the L infinity norm, because this is a minimizer for the L infinity norm. So will be a minimizer for the L infinity norm. It will be stationary for the L infinity norm. And we see it, the next exercise that I give is that stationarity is a continuous operator. So you can always, if you have stationarity here, you can pass it to the limit. And so this will be stationary for the L infinity norm. And indeed, what we will see in the third lecture is that for more generic energies, this theorem is true if and only if the integrand is strictly convex. And indeed, the L infinity norm is not strictly convex, it's just convex. Actually, this is a kind of a summary of the situation. Yeah, but for the area, this is not a stationary varifold. Sorry? So I think that if you make a deformation that such that the differential let's say flatten up this variable, this tangent plane, this in this derivative makes better. Yeah, it's a it's a compression. Yeah. You cannot do really projection, but it's enough in infinitesimal deformation that flatten up the x. So you will want to get closer and closer to your real tangent line. So this, if one does the computation, yeah, you will see that something like this, you cannot really do it as a projection, but something like this will, or if you want also something like that, because it's, yeah, thanks. The delta coincidence. Yes, and if you want, this is a consequence a consequence of Alla rectifiability theorem. Really to shoot far, but I agree. You can show this very easily just by looking at. There are actually plenty of ways. Okay, probably I have a simpler way to see this. Is that if you look at the first variation away, rather than making computation with x, the first variation you can see it as the gradient of your vector field tested against the t, where t is the tangent plane at almost every point. And this is in dv and in d mu, where mu is the disintegration. Sorry, d mu t. dvx and d mu t. So up to blow up, you can imagine that mu is constant. It doesn't depend in x. So if you do an integration by part here, so if you do an integration by part there, in a sense, you get some direction of invariance. And the direction of invariance implies something on the measure mu. Actually, we will do this kind of computation later. So yes. Yes. The first variation, the weight. Yeah. This is what I was saying to Giovanni like before. I was saying to Giovanni that actually this is a theorem that it can be localized. So you can this theorem can be easily localized. So you can take your varifold, you restrict it to the set of points which has positive upper density, and that part becomes rectifiable, and all the rest you can forget. And the reason is because the first since these points are there is a splitting between these points. If you look close at this point, you can kind of ignore in the first variation being equal to 0, you can kind of ignore the other part. So you can really localize the result. Yeah, that's a very good point. Yeah, thank you for the comment. Any other question or comment? Okay, so very good. So a couple of other things before we move forward. Okay, let's say this is a very easy exercise, an exercise for you. The first variation, oh, I didn't say something. That guy, so this guy is also denoted as first variation. In general, you call this guy the first variation of the varifold applied to X, just by definition, independently of whether it's 0 or not. So an exercise is that the first variation of X can be written in integral form as the integral on the Grassmannian bundle. An integral on the Grassmannian bundle of the divergence, the S divergence of X in the VXS. Where this guy is simply it's just a notation, as I was writing also there, is the gradient of X inner product with the plane S, which by definition is just the sum of the scalar product between tau I and the gradient with respect to tau I of X. I from 1 to, this is the dimensional D, and tau I, as you can imagine, is an orthonormal basis. An orthonormal basis of S. Okay? So this is an exercise. The reason why I want to show this is just to get back to one small thing that I said before, that the first variation is a continuous operation. So when you have 0 first variation, you can pass this to the limit. So remark, if you have a sequence of d-varifold Vj such that dvj is equal to 0, and Vj converges to V, then the first variation is equal to 0. Okay? And once I give you this geometric representation, this is kind of obvious because it's just a test. It's just a test, right? So you just say, well, 0 is equal to dvx. This is just testing V with the map divergence as X. And now you can use weak star convergence. So this is, sorry, let me add the J here. And this is just V divergence as X. So this has to be equal to 0. And this is also the first variation of V applied to X. Okay? So since this is true for every X, you get that the first variation being 0 passes to the limit. And more in general, so I will do computation in this course for stationary varifolds, but more in general, what I say will be true also for varifolds which have local bound on the first variation. So locally bounded first variation. This a varifold has locally bounded first variation for a varifold V if there exists a constant which depend on the compact kappa, on a compact set kappa, such that the first variation of the varifold V applied to X is bounded by the constant depending on kappa times the C0 norm of X. And this is true for every X that are C1 compactly supported vector field. With the extra thing that the support of X should be in kappa. Okay. So basically what we are saying is that essentially if you have a locally bounded first variation, the first variation is a continuous linear operator in this space. And in particular, you can apply Ritz representation. So in particular, by Ritz, you know that there exists H, vector valued measure. It's a vector valued measure on Rn such that let me use the last space I have, such that the first variation of V applied to X is equal to minus the integral on the Grassmannian bundle of the scalar product between the vector field X and nu in the oh, sorry, this is not the Grassmannian bundle, sorry. The integral in Rn. In Rn, in the total variation of H, where, as you can imagine, nu is just the derivative of H with respect to the total variation, where nu, d nu is just dH derivative of H over the total variation of H. Okay, this is just the representation theorem. So in a sense, you can interpret the first variation when it's locally bounded. When you have locally bounded first variation, you can interpret first variation as a distributional mean curvature. Okay? Yes. Yeah, because it's an order one distribution in the meaning that in the operator you have the gradient of X. So you at the end you end up bounding in the C0 norm. So it's not with respect to the C1 norm of the Okay. Pretty good. Oops. And just a small exercise on this for you. If you have a smooth manifold, if sigma is smooth and compact, if sigma is smooth and compact without, well, let me say also without boundary, because otherwise there are extra terms appearing, because the boundary always gives a singular part of the first variation, then dH is exactly the H of sigma in DHD restricted to sigma, where H sigma is the classical mean curvature. Okay, so it just reflects the standard computation. How much time do I have? Sorry? 10 minutes? Okay, perfect. Also, now that we have done all this, I just want to make a small observation with the difference between convergence of current and convergence of varifolds. Just a small other observation. This is an example. Currents versus varifolds. Currents versus varifold. If you take this, if I give in R2 the interval 0, 1, the interval 0, 1 in R2, and let's say that at 1 over 2j, I put a little ball here, say a bit detached, say of radius 1 over 2 pi j. Then this is 1 over j. Then again at 3 over 2j, I put another little ball of the same radius, and I orient all these balls counterclockwise. Okay? So this Tj, these curves, let's call them sigma j. If you look at them as currents, Tj, they will come, and I do this up to the point 1. So I have all these little balls. If you take a limit in the sense of currents, you converge to 0. This is a simple exercise, right? Just because if you compute the flat norm of this Tj, here you have these fillings that have mass, say j from 1 to L, where L is the amount of points you... sorry, just the circle. So for me, the Tj is the union with the I from 1 to L of the boundaries of this point. Let me give a name to them, PJL, of radii 1 over 2 pi j, oriented counterclockwise as a current. These guys are converging to 0 because the flat norm can be bounded just by the fillings, and the fillings are just of area pi r squared, which is 1 over 2 pi j squared. Right? So this is 1 over 4 pi j, which is going to 0. But if you look as in the sense of varifolds, which means I just forget of the orientation, if I look at these varifolds, it's very easy to see that, actually the exercise for you, exercise is super easy. It's an homogenization procedure, so you will invade homogeneously the whole line. What will be the mass? Well, each of these has length 1 over, as radius 1 over 2 pi j, so as length 1. So you are as length, 1 over j, and you are summing these guys. So the total mass will be 1. So you will converge to 1. H1 restricted to this interval, 0, 1 times 0. And the nice thing is that the Grassmannian part, this is also easy to see as an exercise, will be the Haar measure. So will be the uniform probability distribution on on G1. Okay? So alpha is R measure. R measure is just the uniformly distributed. The R measure on S1, on G1, sorry. Okay, so this is an easy exercise you can try to do with test functions. Okay, so this really identifies the difference between currents and varifolds. You see, the thing is that all this orientation in the limit are kind of canceling out as a current, while as a varifold you will keep just the same mass. Okay. Pretty good. Okay, now I don't know how much I will be able to say about this because I have 5 minutes left. So, but a cornerstone property, you will see along all the lectures that the cornerstone property of stationary varifolds will be the famous monotonicity formula. Don't know how much I can say today, but let's just start. So monotonicity formula for stationary varifold, so for varifold with first variation is equal to 0. But in order to ease in this formula, let me do this for d-dimensional embedded submanifolds. Sigma, that is d-dimensional embedded smooth manifold, submanifold. Manifold which is also locally area minimizing. Locally area minimizing. Locally area minimizing just means for me that for every other surface d-dimensional manifold sigma hat, let's call such that the symmetric difference between sigma and sigma hat is compact. Then the area of sigma in kappa is less or equal than the area of sigma hat in kappa. Okay, the reason why I have to introduce this thing is because sigma may be not bounded. So if you have this property of locally area minimizing, and I do this property because the proof is kind of the same in the stationary case, it's just it uses the same idea. Okay, so if you take a point, this is your surface sigma, you take a point P in Rn, P in Rn, P in Rn, P doesn't need to be on your manifold. It can be any point. So you take a ball around this point, BRP, and you call gamma RP or gamma PR. So let me use the same notation. The slice, so sigma intersected with dBRP. Okay. So more SARD lemma tells you that for almost every R positive, this guy is a C1, let's say D minus 1 submanifold. D minus 1 dimensional submanifold. Okay. And what you can show by the coarea formula, by the coarea formula, you can show that the D minus 1 dimensional area of gamma PR, which is basically in this picture, these 2 points here, okay? Of course, in a higher dimensional case, you see it better. For instance, in 3D, this is a curve. This area is less or equal than f prime of R, where I have to tell you what is f, where f is just the area of your surface sigma in the ball of radius R. Okay? Where f of R by definition is the area of sigma in BXR. This is by coarea and is essentially telling you it's a less or equal just because your surface, if it's transversal sigma, of course, by coarea, you get an area factor that is like 1 over the norm of the projection on the tangent space to sigma of x over norm of x, right? So this is the area factor that you get from coarea. And this guy, clearly the denominator is always less or equal than 1, and is equal to 1, the denominator, just when sigma is completely orthogonal to the boundary of the ball. So in this case, this guy is 1. Otherwise, this guy is, in principle, bigger or equal than 1, and this gives you this inequality. Okay, so here equality, if and only if sigma, let me say, orthogonal to dBXR. Okay? And can I steal 1 minute? So just to close the computation. And then what you do is that you take your surface, say P is here, you replace sigma with a sigma hat that basically inside the ball replace sigma with the cone that has the same trace of sigma, okay? Let's call this cone CPR. And now it's a simple computation because the area, for me, CPR is just the things that is inside the ball. The area of CPR is just D over R. Oh, sorry, R over D. Otherwise, it doesn't scale. R over D, HD minus 1 of the trace, but the trace is gamma PR. Okay? This you can show again using coarea formula. And now you use the local minimality to say that now you use the local minimality of your function, of your sigma, the area minimality, to say, well, f of R is the area of my surface sigma in the ball of radius R, is by the fact that you are locally area minimizing, is bounded by HD of CPR. But HD CPR, we just said that is equal to R over D HD minus 1 of gamma PR, and this is equal to R over D. So this is less or equal than R over D times F prime of R. Okay, so you have a formula of this type. F prime over F less or equal than F prime over F bigger or equal than D over R. In particular, you get the derivative in R of log F plus minus log of R power D is bigger or equal than 0, which tells you that the derivative in R of the logarithm of F divided by R power D is bigger or equal than 0. And since the logarithm is a monotone function, then also F over R power D has bigger derivative that is bigger or equal than 0. And remember that F was just the area inside the ball. So we deduce that the density ratio is non-decreasing at all scales. Okay? So in next lecture, sorry, I stole 5 minutes more. I'm very sorry. But from next lecture, we take it from here. We see what it means also for stationary varifolds, and we build our theory starting from here. Again, sorry for taking 5 minutes more. Thank you.
So, questions? Okay. If there are no questions, then we thank you again. Welcome everybody to the last lecture today. And the speaker is Marianna Csornyei, and she will talk about Kolmogorov complexity and geometric measure theory, more or less. I'm not sure I remember your title correctly.
I don't remember it.
Okay, fine. So it's correct. Please go.
Okay, so we have 3 other people in the room except for me, and I will be speaking to them. But I think it's better than to speak to the screen. But one of them is the main expert in this area. So if you ask some questions in the chat, he will be able to answer, or if it's a short answer, or he can tell me that there are some questions that I should answer. So these talks are about applying some methods that comes from computational complexity or solving problems in geometric measure theory. And my main aim for today is just to explain the basic definitions. So there will be one proof, one not completely trivial proof, but everything else will be a definition. So this is something very new, and the whole story started. So the first paper about this is a better one. So this is from 2018. So when 2 people called Lutz, Jack Lutz and Neil Lutz, so they published something which is they called point to set principle. So what this was, it's really an equivalent definition of the usual Hausdorff and Pecking dimension. Sets in Rn, but it wasn't the usual definition. They were using methods from complexities. So can you read what I'm writing? Is it okay? Can you hear me?
We can hear you well. And if you could write slightly larger, that would be perfect. So when you write in capital letters, that's fine.
I will try my best.
Yeah, thanks.
Okay, so I don't know if these two Lutzes are related to each other. Don is nothing, so it's father and son. But to make things even more fun, there is a third Lutz working in the same area. So there is also Patrick Lutz, who is one of the main experts, and he is not related to them. He's just sharing the same surname. And so a few more names I should mention. So there is Jacob Igler. So he was an undergraduate student here in Chicago, and this first paper that was published by Lutz and Lutz, this really appeared in a computer science journal, and nobody in analysis or in geometric measures really know about this. So they didn't know about this in that time. It was really only people working in computer science or logic. And one of my colleagues who was working in logic gave this as a project to Jake. So he knew that Jake was excited about my lectures in geometric measures theory, and then his task was first to read the paper, and secondly, it was his job to explain it to me. So he did, and I must admit in that time I wasn't very impressed by this thing. So it looked like a fun fact that yes, you can define dimension using these things, but I didn't think of it as something very deep or something that can be used to do interesting mathematics. So this changed about 3 years ago when I saw a paper of Donald Stuhl. So what he did in this paper, it was about the four-corner distance set problem, which I may speak about later. And in this paper, he proved a better estimate for the dimension of the distance set than what was the best known estimate in that time, using this complexity stuff. So that was when I got interested. I was trying to read the paper and I couldn't. And then I looked and I saw that there were other deep results published by this group of people that I couldn't read. And then I so the short story is that I sort of kidnapped Don. So he is now my postdoc, and I learned many of these things from him. He used to be somebody with a computer science background, but by now he's a mathematician with every possible means of the word. So officially he's my postdoc, but in practice it's more like I am his student learning these things. So he's the one monitoring the chat. So feel free to ask any questions. And now these names I listed, these are really the people proving the main results. And I think Jack Lutz was the advisor of Don. Yes, and everybody else is either a student or a postdoc. And there are a couple of more names I could add, but there's also very young people. So it's a young field. So now let me start with the definitions. And the first thing, of course, which I should explain is what do I mean by complexity? This will be Kolmogorov complexity. I would like to show you two versions. So one is the heuristic token. Well, this will be explaining how I personally think about Kolmogorov complexity, which is not the same as people working in this field are saying or writing in their papers, but it's something which is easier for me. And then later I will also tell you something about the formal definition. So this is a little bit like, we all know what a set is, but if you really want to know what a set is, you have to do axiomatic set theory. And there are some issues like the set of every set is not a set. And similarly, there are some issues with Kolmogorov complexities, but these are not things that you would be worried about on a daily basis. You just assume that you know what a set is, And unless you are a set theory, so a logician, you don't really care what the formal definition of a set is. So this will be something similar. I will give you two definitions. One of them is correct, the other one is less correct. But at least for me, the less correct one is much more useful to think about. So let me start with the less correct one. So X is a finite sequence of zeros and ones. And I will denote by X bar the length of the sequence. Now my informal definition, so K of X, this is the Kolmogorov complexity of X. So this will be really the length of the shortest sentence. Describing what X is. So when I say the length of the sentence, since everything comes from computer science, I have to encode this sentence using zeros and ones, which is easy. You just assign to every letter or to every symbol a finite sequence of zeros and ones, say of length 10, and then write down these sequences. So this shortest sentence, this is encoded pretty much in any way you like, using zeros and ones. So let me show you some examples. So what I mean by this. So for example, if X is a sequence of length n, then I can always say that the digits of X are zero, one, 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 zero, one, zero, and so on. I just write down X. Of course, this is a perfectly valid way of defining what X is. And what is the length of the sequence? So when you encode the beginning of the sentence, it will have some length. We don't really care what it is. It's a constant. And the length of the second part is the length of n. So this shows that K of X using this definition is always at most n plus a constant. This is true for every sequence. And the fact is that in general, you cannot do much better. So if you have some random sequence of zeros and ones, there is no really any special pattern or rule that they follow. It will be actually a theorem that you cannot do better. But sometimes you can. So another example is, say, X is just 0, 1, 0, 1, 0, 1. Every second digit is 0, and every second digit is 1. So for this, I can write down the sentence that it's a sequence of length n. And I just say that every odd digit is 0, and every even digit is 1. So what is the length of this sequence? So the only thing that may take a long time to write down is what n is. Everything else is a constant. And to write down what n is, since we have to use zeros and ones, so the number of bits we need is like log n. So for this particular sequence, kx is at most log n plus a constant. So are there any questions? So this is something that people in computational complexity may be interested in, but we are not doing discrete mathematics. So now let me go to the continuous version. on our X is a point in RD. Then we define its cohomology of complexity. So K and X will be the cohomology of complexity X with precision N. So what is this? I just take diagonal Q. So let's for simplicity assume X is inside the unit. And then let Q be the diagonal Q, a unit diagonal cube containing X and of size 1/2 to the n. So that's where the precision n is coming from. And the diagonal cube is very easy to encode using zeros and ones. So we encode this. We get what? So it's a cube of size 1/2 to the n. So I need n digits for each of the coordinates, and there are d coordinates. So encode this into a sequence in the most natural way. Length d times n. And then k and x is the complexity of this sequence. And then everything will be based on, so what we will be studying is how fast this increases as n goes to infinity. That's the main question for us. So first definition, which if you haven't seen this before, it looks very strange. So I say that the Hausdorff dimension of a point x is a point in RD. This is the limit n goes to infinity, k and x over n. And the packing dimension, the mean soup for the same thing, k and x over n. So this is Hausdorff. This is packing. And now this really looks like nonsense. I mean, no matter what definition of dimension you are using, a point should always have dimension 0. Otherwise it's too stupid. So somehow and here using this definition, both the Hausdorff and the packing dimension can be anything between 0 and d. So the important remark that there is a difference. The dimension of x, when x is a point in Rn, this is really not the same thing as the dimension of the set that contains only one point. These are really two completely different notions. And this can be anything using this definition between 0 and 2. 0 and d, this is always 0. So as you would expect, the dimension of a set containing a single point is equal to 0. So the idea is that in general, we try to find dimension of a set using information on the dimension of its point. But the dimension of a point is not the same as the dimension of a set which has only one element. So that's the definition. And now let's do a little proof. So this is like the first exercise. Basically, it says if a set has large dimension, then it must contain some points with large dimension. So more precisely, my claim is that if E is just a set whose points in RD whose dimension, a Hausdorff dimension of X is at most some number S, then Hausdorff dimension of E, the usual standard Hausdorff dimension of a set, is at most S. So in other words, if E has dimension larger than S, it must contain some points of dimension larger than S. So this is really an easy exercise. So let's see why it's true. So if X is in E, so it has this dimension less than S. What does that mean? So in this case, X is covered by some dyadic cubes for which we have some upper bound of their complexities. X is covered by some dyadic cubes such that their length, their size is 1/2 to them, and their complexity of the sequence describing the cube, this is at most, and if this limit is at most S, then Kn(x) is at most Sn times 1 plus epsilon, or some positive epsilon. And this is true, so we can find such a cube for infinitely many n. For any given x, there are infinitely many n with these cubes. And now really the only thing that uses complexity is the clear remark. So this was the definition of complexity of a sequence, the length of the shortest sentence written in zeros and ones. Now how many sentences I can have of length, of a given length? That's the only thing you need to know about complexity, is that the number of sequences of zeros and ones of length k is at most 2 to the k. So that gives us an upper bound on how many cubes we can have of a given complexity. So now what we know is that there are at most, in all the whole world, there are at most 2 to the s. So I'm looking at sequences whose can be defined by a sentence of length at most Sn to the 1 plus epsilon. That means that I have at most 2 to the Sn times 1 plus epsilon many cubes of many cubes like this. Many cubes with that complexity. So if I try to calculate the Hausdorff measure, so I sum for every cube the size of the cube to the power s times 1 plus epsilon. Or actually, let's do the 1 plus epsilon prime. It's some epsilon prime, which is slightly larger than epsilon. So this is now what? So you have to look at all sizes, so summation for every n. And for a given n, I have at most this many cubes. And this will be, for each cube, it's 1/2 to the n to the power s times 1 plus epsilon. Right. And as you see, Sn is cancelled, so this is summation for n Then you have 2 to the Sm of epsilon minus epsilon prime. So this is finite for every epsilon prime larger than epsilon. And that, of course, means that the house of S times 1 plus epsilon dimensional house of is finite. And then indeed, since this is true for every epsilon prime, get that. So it's really a very simple argument using very standard things. The only new ingredient is that we count how many sequences we have of length n, how many sequences of 0 and 1 of length n. Okay, so this was the easy part. I would like to explain something which is for me, it took a much longer time to understand. And this was what oracles are doing. So what is an oracle? That's the next question. So this was hard because the only thing I saw was the formal definition, and I really had to come up with a definition I can understand much easily. So what is an oracle? So in ancient literature, an oracle is a very mean woman. And you can ask questions from her and she will give you some answers, but these answers can be interpreted in more than one way. And the obvious interpretation is wrong. And then the hero dies. That's what always happens. But that's not what will be happening here. So there won't be any blood involved. An oracle is something for which you can ask only yes or no questions. So there is really no way of cheating in any way. And actually, I would like, this is what everybody always says, that an oracle is something you can ask complementary yes or no questions from. But my way of thinking about it is that it's really countable information. That we can use for free. And then provided that we know this countable information, now we can ask what is the shortest sentence defining X. One example. So say I have a circle. C is a circle. And knowing what the circle is, this is a countable information because I just have to tell you what is its center and what is its radius. So these two numbers you can encode in binaries. So I just have to tell you what are those countable many zeros and ones. So this will be the oracle that I use. That I assume that I already know the circle, but now I'm looking for a point on the circle. So want to find some points on the circle. So in principle, since most points have big complexity in the plane, circle is in the plane. Most points have complexity 2, and there is no reason why this circle will not contain some points of complexity 2. But what I claim is that if once I know that X is on this circle, that pushes down the complexity to 1. So since I already know the circle, I just need to tell you, just need to define angle. So here's the circle, this is X, this is an angle theta. If you already know what the circle is, if I tell you what theta is, you will know what the point is. And now the key fact is that the circle is a one-dimensional thing. So similarly, as I showed you before, that in RD, every point has dimension something between 0 and d. Just by the same argument, every point on the circle will have dimension. You can write down. So basically, I identify the circle by R. I think of theta as a real number. And then I know that every real number has complexity at most one. So this is the notation. The dimension of x, and then writing after index the circle, provided that you already know the circle, this is always at most one for every x in C. So are there any questions about this? Can't hear anything. So the next observation is that this argument actually has nothing to do with the circle. It doesn't have to be a set which you can easily describe, like saying what its center is and what its radius is. So here's a more general example. So let now E be an arbitrary set. And I assume also dimension. Yes. So what does this mean? It means that we can cover E by dyadic cubes. Such that when you add together the powers of the size of these cubes with some exponent which is slightly larger than s, then you can make this sum arbitrarily small. You can cover it by something where the sum is at most epsilon, and then you can also find another covering where it's at most epsilon half. You can cover it again such that it's at most epsilon over 4. So altogether, we can cover it by cubes such that, say, the sum of the size of the cube s times, I want to put that number epsilon here instead of just s. This is, say, bounded by 1. And also, every x is covered by infinitely many of them. So this is something we can do with every set that has dimension at most s. And now if I want to tell you what a point in E is, a point x with precision n, if there is if one of the cubes do cover it, and it has size 1 over 2 to the n, then I just have to tell you what that cube is. So the oracle we use will be just all the cubes we use in this covering. The cubes of the covering. So this is the count of the information I want. I want to know this count of many cubes that I used in the covering that does this. And then using this oracle, if I want to define x, so if x is, say, inside the case cube of size n, and I know which cubes I use of size n, I know which one is the case one, then this is a valid definition. I can just say x is inside, I'm speaking of the x, which is in the case cube of size n. This gives me what x is with precision n. So Kn of x is at most the length of this sentence. So Kn of x is at most, so what is the length of this sentence? It's a log k, there is a log n, then there is some constant. So which one of the main term of it? Actually, it's log k, but I can have many cubes of the same size. And I have an upper bound how many? So I know that this sum is finite. So this log k, this is really the log of the number of the cubes in this covering, such that the size of the cube is 1/2 to the n. And since I know that if I raise the power less times 1 plus epsilon, I get at most 1. So this is at most log of how many cubes I can have, 2 to the ns 1 plus epsilon. Because this multiplied by the number of, by the diameter of the cube to that power is at most 1.
So 1/1%.
Sorry? Okay, so when you take log, whenever I take log, it's log in base 2, first. And then this is really a linear term in L, this is a logarithmic term, and this is a constant. What we're interested about is what happens if you divide everything by n and take the limit. So obviously, okay, sorry, I forgot that A here. So A is this oracle. Using this oracle, the complexity is at most this one for infinitely many n. This is true for infinitely many n because every point x by was covered by infinitely many cubes. And then what you get is that the dimension of A, dimension of x using A is the limit of this thing divided by n, so it's at most s times 1 plus epsilon. And now what we did, so first we chose an epsilon, a positive epsilon, and then we chose an oracle that depended on epsilon. So I now want to get rid of this dependence. I want to get an oracle that doesn't depend on epsilon, and that's the same thing. So I wonder, other than Don, can anybody see why is this true? That actually, we can assume that the oracle doesn't depend on epsilon.
Wait next to the epsilon, maybe?
Sorry? Say it again?
You kind of wait next to the epsilon in the smaller, since like count on things.
Yeah, I don't know if people heard it, but it's really just countable of countable informations is a countable information. So if you have a sequence of oracles, you can always, so for each epsilon you have an oracle, so you have, let epsilon go to 0, you have a sequence of oracles. You can just take the union of these oracles. That will be just lowering the dimension, that you have more information. It won't be increasing it. So in fact, A can be the collection of every cubes used and for every epsilon from your sequence of epsilon going to 0. So a corollary of this, this is the main theorem. So if E is a set naive, then the dimension, also dimension of E, is really the same. Choosing the best oracles, taking the minimum for all oracles, and then the supremum for x free, and the dimension of x is in this oracle A. Everything, even if I forgot to say this Hausdorff dimension. So I claimed this was what this proof did. There is no interest bit more. There is also a similar statement about packing dimension. Packing dimension of every set. Only thing we have to change is the packing on both sides. Right, the packing dimension of x divided over A. Which simply means instead of a lim inf, I take a lim super. If the limit exists, then they are the same. So that's what Lutz and Lutz called the point to set principle, which a name I It's a name I don't really like. I just call it the theorem. Or if I want to give it a name, it's the complexity characterization of dimension of the set. So the second one I leave it aside for exercise. And the students who are in this lecture in Chicago, they will get a chocolate if they give me the solution tomorrow for the lecture. I don't know if the organizers in Italy will give chocolates to the participants. That's up to them. But I can give you a virtual chocolate. And okay, so it's not a chocolate problem because it's hard. It's really as easy as for household dimension. It's just to get you to practice these things a little bit. So why is this true for the household dimension?
What's the problem?
Sorry?
What's the, the packing.
So the homework problem is to do it with packing, and I am doing it with household. So let's look at what we have just done. We have just seen and there is for a given E, there is an oracle A. Such that using this oracle, the complexity of every point is at most S times 1 plus epsilon. And this was true for every epsilon for every X in E. And of course, this means star so S was the household dimension of E. That means that the household dimension of E is always at least that is on the right hand side. So we show that the left hand side of star is always larger equal to the right hand side. Now, what about the other direction? So basically, I'm saying that no matter which oracle I use, there will be always some points in E of high complexity. That's what left-hand side less equal right-hand side means. So we have already seen this statement without oracles, but now we have to check that the same is true with oracles. So this is the same statement. If a set has large dimension, then it must contain some points of large dimension. So we have seen a proof of this without oracles. And as I was emphasizing, this was a very standard basic proof. And the only thing you needed to know for this proof is that there are at most 2 to the n sequences of zeros and ones of length n. And now I want to copy the same proof using an oracle. So an oracle can somehow decrease the complexity of points, but not too much. No matter which oracle you use, there are still only at most 2 to the n things you can say. There are at most 2 to the n possible valid definitions of something of length n. So the same thing is true that we will have the same upper bound on how many cubes you can have of the given complexity. The upper bound that was in that proof, which I don't remember, and I had some epsilon prime, is exactly the same with or without an oracle. Because the only thing that it used is that how many definitions you can have of length n. And even if you can use this quantum information for free, you can only write down 2 to the n possible definitions of length n. So really the proof is the same, and proof is the same. and with oracles was before. Without an oracle. So I hope this is okay, but if you want me to explain it more, then please tell me. So this proves point to set principle. And again, what is a good way of thinking about this? So let's just look at this statement. And somehow the idea is that if you have only one point, you can always encode it in an oracle. Oracle can just tell you what the bits of X is. And then everything becomes trivial. So defining X, you don't have to do anything if you know already what X is. So the complexity of a set that contains only one point is obviously 0, because you can just choose the oracle which tells you what the bits of X are. And you can do the same with count many points. But as long as your set E has more than count many points, this argument doesn't work, because you are free to choose any countable information you want, but you are forced to use the same countable information for every point X. Your countable information cannot depend on which point X you are looking at. And so you try to optimize this, you try to find the best countable information that lowers the complexity of every point, and how far down you can push the complexity using the same countable information for every point X. That's exactly the household dimension of the setting. That's the meaning of this statement. Okay, so now I think it's time to turn to the formal definition. So to do things correctly, there are two things I need to be more precise about. The formal definition. Formal complexity. There are two things we need to understand. The first one is, what is an oracle, really? What do I mean when I say this kind of information can be used for free? And this actually may look complicated, but it won't cause any problems. So this will be the easy part, easiest thing to understand. And what is much more tricky is, what is a definition? Finite sequence of zero mass. And this is much more tricky. So we think that as mathematicians, we think we know what a definition is. We don't have any doubt whether something is a definition or not. That it's a similar type of thing as we don't have any doubt whether something is a set or not. And unless you are a little bit careful, you run into problems. So let me write down a definition which causes that. So let's just order sequences of zeros and ones in the natural way. So first I have 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and so on. Each of these sequences has some complexity. And then I just say, take the first sequence. That doesn't have a definition using less than 1,000 words. Does not have a definition. Using most 1,000 words. So I guess you can see the problem is I have just defined this x using the sentence I wrote down, defines this x that cannot be defined using less than 1,000 words. I just did it. I defined it using less than 1,000 words. So this is a problem. This is a bad problem. This is a serious problem. So this is a contradiction. Something is wrong. You cannot define a sequence by less than 1,000 words, and you can at the same time. So I really have to do something different. And I really want to explain you what the definition is. And some definitions will be valid, some definitions will be not valid. And this won't be a valid definition, according to when I tell you what the definition is. So, the idea. I do something different. Maybe the best way of explaining this. So in comolar complexity, so replace shortest definition by shortest algorithm without these x. So you have a sequence of zeros and ones, and you want to find a computer program written in your favorite language that the computer program does. It writes down what x is. And to do things formally, so I would need to define what I mean by, before I didn't know what the definition was, and I don't know what an algorithm is. So this doesn't look like something useful, but actually, those of you who know some logic, everything can be defined using Turing machines, which I won't do now because this is not a lecture on logic. If you are interested and you are not too lazy, you can learn this. You can find it in many places in the literature, but our heuristic picture of an algorithm is actually correct. It's an algorithm, but what does it do? So it's basically just, depending on where you are, the algorithm tells you what to do next. There are some rules of the game, and everything is completely determined. Depending on where you are, the rules will tell you where you move to. That's what an algorithm is. That's what every computer program does. It's a list of instructions, and you follow these instructions and behave accordingly, then you run that computer program.
And by shortest.
Yes, so thanks. That's an important to point out. So we need to encode every algorithm. We need to encode using zeros and ones. And when I say shortest, so many times when you study computer science, they look at how long an algorithm lasts. But that's not what we are doing now. We don't care whether it stops soon or it stops only after a very long time. What we do care about is really how long it takes to write down the computer program. So the computer program, the program itself, encoded in zeros and ones, how long that program is. And then for those of you who know Turing machines, you actually have to look at not just any Turing machine, but a universal Turing machine. So that's something that can run other programs. Program that can run other programs. You want it to be optimal, which means it will calculate everything almost as a short program as is possible. The difference will be small error. And also this is boring if if your algorithm or your computer program is just having fun by itself. You want it to communicate with the world. So actually what it does, depending on where you are, and depending on what you tell it, and depending on an input, tells you what to do next. So when Turing defined this, it was, everything was on tapes. So imagine an infinite tape where you can write zeros and ones. So this is from the time when every information was stored on rolls of paper. So just think of, these are rolls of paper, and you can give your computer program a roll of paper with a finite sequence of zeros and ones, and there is some head moving along this tape. And depending where you are, and depending what the head sees a zero or a one or nothing, it tells the program what to do next. Which next stage to move in, and what to do on the tapes. Write a zero, write a one, delete what was there before, move to the left, move to the right. There are some well-written rules about this, what the program should do, and those are the rules that we encode using zeros and ones. So this is something that real-world computers do, but now we also allow what the program does depending on its program, depending on the input, and depending on an oracle. So that's something that needs an explanation. What do I mean by an algorithm can use an oracle? So what an oracle is. So before I said that it was a countable set of informations, but now I say that oracle, this is really a set of finite sequences zeros and ones. So think of this like yes or no questions. If sequence is in the oracle, then we say yes. And if a sequence is not in the oracle, then we say no. And what the computer program is allowed to do is that each time moment it's somewhere, it sees an input, but one of the possible places it can move to is asking whether a sequence is in the oracle or not. So first he needs to write down the sequence, otherwise he's cheating. So the computer program already wrote down a sequence, and then it can enter a special stage, which is now you can tell the program, now ask the oracle whether this sequence you have just written down is yes or no. And if yes, then do this. If no, then do that. So this can be part of your computer program, that your program is allowed to ask an oracle about any sequence, whether it's in the oracle or not, and depending whether the answer is yes or no, it does something which was determined before, what it does if it's yes, what it does if it's no. So this is the definition with oracles. And now the key fact. So we had my fault. So we had a definition before of coverable complexities that had a serious issue. And this came from writing down an invalid definition that led to a contradiction. And now the key fact is that there is no algorithm that would find the first X. First finite sequence. Which has high complexity, so its complexity of X is given then. Let's say larger than this. So this complexity is now defined as the length of the shortest computer program. Its output is x. And there is no way to write down an algorithm that would find those points for which there is no short computer program. So you may think there is. So what is the obvious thing to do? Let me try to write down an algorithm. It's a remark. For every program of length more than 100. So remember, there are finite many of them. Run that program. And look at their output. List all the outputs. All these finite many outputs. And then find the first x which is not on the list. So this looks like a good algorithm that would find you the first one with high complexity. So really my question is, why is this not okay? Can anybody see, right? Why is this not okay? So the issue is that there are computer programs that never stop. You can enter a repeat cycle or something, and you try to run every program of length at most 100, but this, provided 100 is large enough, you will find some programs that never finish. They're just waiting and waiting and waiting, and it's an algorithm that never ends. And you will not know what are the outputs of every program because you don't know whether later that algorithm will stop or it won't. So the answer is that they may not stop. They may never stop. And this is again something that logicians love. I mean, looking at the halting problem, which sequence this can be defined by program sets, which sequence cannot be defined. So the issue is that the set of those points x for which there is a computer program of length at least 100, this is not something you can find. Okay, so let me just write down the last thing I said in words. So the main issue is that this is a fact which I want to prove. You just need to believe me that it's not possible to find. You cannot find those x. By an algorithm whose complexity is at least something. And this is why the definition, let's take the first x whose complexity is big, it's not a valid definition. So this is one fact. And another one is that, but we can find those x whose complexity is at most a constant. So you can always use upper bound and you're not allowed to use lower bound. And this looks like a fun fact, but this is actually important. I will use this in tomorrow's lecture. It will be super important to know those points whose complexity is bounded from above, this is a computable set. Although those points whose complexity is bounded from below, that's not.
You say the second one is numerable because we can only.
Yes, so there is a computer program with. Okay, I will explain this a little bit more later. But the fact is, if you have a computer program whose output is a set, that doesn't mean that you have a computer program whose output is the complement of the set. That's not true in general. Okay, so I have to find the last page. Okay, so this was the key fact, which is still here. Now let me write down the key happy fact. This was some of the unhappy fact, and now the happy one. So this is that our heuristic definition is okay. If you don't do anything too crazy. So if you can use in this definition, k of x, the shortest definition of x. I have to tell you what I mean by definition, and we cannot do something too crazy. So provided that the definition is computable. So what I mean by this, so let me show you first an example. So let me go back to the circle example. That was an easy one. So we had a circle and a point x and an angle theta. And what I was doing, I said that I was defining x using the circle and theta. So our definition, what it does, it gives us the circle and the angle. And we want to find x with some precision. Everything, the circle is given with full precision. The angle and x, yeah, with some precision. So obviously, there is a very easy way of doing it. If you know the center of the circle, you know the radius of the circle, you know the angle with some precision, it's very easy to write down a computer program that calculates you what the dialectic cube of x, that is the dialectic cube of size m that contains x. So this will be a computable definition because there is a computer program that given c and theta, it calculates what x is. But you cannot do something very crazy. So this example was okay, but we cannot just parameterize the circle arbitrarily. Cannot just parameterize C in any way we want. So we cannot assign to each theta point x in any way we want, arbitrarily. So then something will go wrong. So what is important that this should be an assignment that a computer can calculate. If I tell you what theta is, I need a computer program that tells me what x is. And if you are using some very crazy assignment, some very crazy parameterization, then you can't And that won't be a valid definition. If you can calculate it, it is a valid definition. If you can't calculate it, it's not a valid definition. So keeping this in mind, that we are allowed to use only valid definitions, everything about the heuristic things were correct. And that's what you would normally do. I mean, why would you use anything crazy? When we are proving theorems in geometric measure theory, this is not really something I would ever be worried about, whether how I define things are valid or not. Unless I really try to do something strange intentionally, it will be valid. But I still have to show, so there is something missing. So now we have two different definitions of Kolmogorov complexity. One is the length of the shortest algorithm, and the other one is the length of the shortest computable definition. So why are these two things the same? Up to a small error, I claim that they are the same. So let's see this. So let's look at K of x, which is the complexity of x using algorithms. And now I know that this is at most the complexity of the shortest definition plus a constant. So here I use, this is the important thing, here I use that the definition is computable. Otherwise it may not be true. So in other words, once I have a computer program of some length that writes down this definition, the length of this computer program is this, I can have another computer program of a fixed length that writes down x. So that's why this inequality is valid. Here is when I use that my definition is a valid one. And now I can continue this inequality. So I told before that there are only 2 to the n sequences of length n. The same is true with computer programs. There are at most 2 to the n computer programs of length n. That's still true, which actually I won't need now, but I will make in the future. But also, the length of a computer program, the shortest one, is not longer than the sequence, because your computer program can't just say, write 001110. So this is bounded by the length of the shortest sequence, shortest definition, shortest valid definition, plus a constant. And now I claim that this is less than the algorithmic definition of the complexity, plus a constant. So why? Because it's a valid definition. I have a program here whose output is x. Then it's a valid definition that I'm speaking about the x, which is the output of the program p. This is a valid definition, and its length is at most the length of p plus a constant. So the best definition cannot be longer than the program. So after these additive constants, which we never care about because anyhow we will divide everything by n, and then let n go to infinity, and we are just interested in the limit and the limit of these things divided by n, these constants won't cause any problem. So the two definitions using algorithms or using shortest valid definition, it's really the same up to a constant error, and then every dimension will be the same. So I am very happy that Don is nodding, because this is something I haven't shown him before. So he seems to agree with this argument. So these two definitions are now indeed the same. And one more thing, another remark. It is now very tempting to encode the meaning of every definition. Every definition into an oracle. What happens then? So maybe my definition is not computable, but I can always ask an oracle which x does this definition define? And then everything may be working. So I will show you that this is tempting, but unfortunately it's not good. But let me explain why it is not good. So first let me explain why it is good, and hopefully you will see the problems. So if I can ask an oracle, whenever I write down a sequence of zeros and ones, I can ask the oracle which x does this define, or maybe the oracle will tell me it doesn't define anything, it's garbage. So let's use this oracle. And I no longer know my definition is computable, but using the oracle makes it computable. Because I write down a definition, it has some length, this length, without an A. So I just use a computer program to write down this definition. Then I ask my oracle, what does this define? That's at the constant, and I found a computer program using this oracle that writes down x. Now the second inequality is, it was a triviality. It's just, you can write that down you could write down every sequence by a computer program which was not much longer than the sequence without an oracle. Of course, you can also do it using an oracle. So this one is completely trivial. And what about this one? So what was the argument here is that, okay, I also want to put an A here, oracle here. So I think this is also trivial. So can you see why?
What's the question?
Why is this inequality valid with an oracle? It's really the same argument as before. So the argument before was that it's a valid definition of x that is the computer program whose output is x. I mean, x is the output of this and this computer program. I just have to tell which computer program. And now I'm looking at computer programs that can use an oracle. So that's the only difference. So why is this argument wrong? So actually, I think that the problem is with the first one.
It's the concept of
What I said sounded convincing, but I don't think it was correct. I see Doris thinking.
I don't like the last inequality, actually.
I don't like either of the two, but I think there is already an issue with this one. So the issue is that what is the shortest definition? When I use an oracle, it may make the definition shorter, and then this inequality is no longer true. So I write down my definition not using any oracle, and I don't know if I am understanding it myself, but I'm speaking about it. I convinced myself this morning that there was an issue with this.
I think there is too, yeah. I think both
Yes,
inequalities,
so we write down a computer program that defines x, and then you use the oracle to find what x is. This is somehow not compatible with the shortest one. Shortest one is not the same with or without the oracle, and that destroys this inequality. So I think the best way to convince yourself is to think about this yourself. But that's why this is wrong. So I have a little bit more time, but I didn't prepare much more for today. I think it takes time to digest this thing. So there is one more thing I would like to tell you about everything, both the heuristic and the formal definition. So when you try to read the papers that people write about these things, you will see a completely different definition. It won't be the one I presented heuristically, it won't be the one I presented formally. And the important difference is that they never look at dyadic cubes. They always look at Euclidean balls in Rn or in Rd. So in every paper there is a more complicated definition, not the same as the one I was speaking about. And Let's call it the official definition. We had a heuristic one, we had a formal one, now that's the official one. Of common of complexity. This is what everybody uses, other than me. I don't even want to tell you what it is, but the main difference is that we have point X in RB. We take a ball around it, and then, so consider rational points inside an Euclidean ball. Around X. And you really look at how well you can approximate the point X using points which have rational coordinates and how difficult it is to write down those rational numbers. So those are finite sequences of zeros and ones. Every rational number can encode as a numerator and a denominator, and you include both the sequence of the zeros and ones. You look at how complex those sequences are, and you try to find somehow the least complex point inside your Euclidean ball, and the definition is based on this. That's the definition that everybody does, and I never ever understood why. I mean, in my mind, the dyadic cubes are much easier, and this was a question I asked many times on the computer scientist, which is very funny that an analyst asks a computer scientist, why do you use Euclidean balls and not just sequences of zeros and ones? That would make everything much simpler. And they always agree that yes, it would make everything much simpler, it doesn't make any difference, but this is not what we are doing for some reason. And they never gave me a convincing reason why would they want to do something more complicated. So I don't know if this is correct or not, but my conjecture is that they believe that people in geometric measure theory prefer balls and they don't like cubes. But that's not the case. We are not scared of dyadic cubes in general. Sometimes they are much more convenient to use than Euclidean balls, and I think this is a clear example when dyadic cubes are much more convenient to use than dyadic balls. Cubes are better than balls. So their definition gives a different number. It's not precisely the same as the definition using cubes, but again, the difference between the two, so complexity of X using balls, difference of this between complexity of X using cubes, dyadic cubes, this will be something small. It will be much smaller than n. It will be a logarithmic term, and then once you divide everything by n and let n go to infinity, the two definitions really does the same. So as far as I can see, there is absolutely no reason to use balls instead of cubes, unless you want to make your life harder. But sometimes Don is trying to tell me something, but I never heard a convincing answer. Why people in computer science believe that in RD, balls are better than cubes. So now he's just laughing.
Oh, did you want me to?
So in these lectures, and probably all my life, I will always use dyadic cubes. I already managed to convince Don that when he speaks to me, he's using dyadic cubes, always. I don't think I managed to convince anybody else. Everybody else agrees with me that yes, it would be better, and then when they write the paper, they go back to the old definition. So, are there any questions? Yes?
What's wrong with if I take a surjective curve from 0, 1 to the unit cube, and I use the exponent choice to pick one point and pretty much every point. But it's showing that the unit cube has unit square has dimension 1.
So I'm not sure what you are doing, that you are saying, but once you use axiom of choice, it's very likely that nothing will remain nice and computable.
But like you can map.
So you can come up with a definition, but it probably won't do the same as the original definition.
Sure.
So of course, you can come up with many different ways of what you mean by complexity, but you want something that you can use to proving theorems in geometric measure theory, and this will be the one I will be using. So, are there any other questions?
We check if there is any question here. We do not have question here. Thanks.
So tomorrow there will be many more geometric measure theory and much less definition and logic. I will show you how to apply these things to prove interesting things in GMT.
Okay, so thank you, and I guess we can thanks in a more loud way.